Hello, and welcome to part one of a three-part discussion of transmission lines. This is a very important and overlooked topic, and I believe it merits a bit of a deep dive. We'll start by revisiting our understanding of how electrical signals get from one place to another, because any electrical circuit will ultimately function only as well as its interconnections. Electrical engineers are first taught a traditional DC or lumped element circuit model in which some source potential is applied, current flows to a load, a potential is dropped across the load, and the current returns to the source. Our focus is on the potential, and we don't pay much attention to the current except as an annoying byproduct of having to drop potential across a load. You know, that old V equals IR Ohm's law thing. This model works just fine at DC and low frequencies, but it runs out of gas when you start to move your stimulus signal at a rate that is faster than the signal can propagate down the line to the load. So, what happens then? I'm glad you asked. We can illustrate the general principle with a simple mechanical analogy with a rope tied down at one end. If I move my end of the rope up and down very slowly, then the entire rope moves up and down essentially as one unit, or as we call it, a lumped element. If I start to move my end of the rope more quickly than the energy can propagate down the line, then we see that the energy is propagating down the rope as a wave. And I've even set up a standing wave on the rope. And the same general principle holds true for electrical signals on a transmission line. The finite speed of electromagnetic waves means that it takes a finite amount of time for any signal to travel down any interconnection, whether it be a wire, cable, printed circuit board trace, etc. When the voltage and/or current on a line changes in a time interval comparable to the time it takes for the signal to travel down the line, the length becomes significant, the signal must be considered a wave propagating down the line, and voila! You have a transmission line. Some rules of thumb: treat any circuit element, whether it be a cable, wire, or printed circuit board trace, as a transmission line if the length is greater than 1/10 of a wavelength for the highest frequency of interest. For anything other than a pure sinusoid, this includes harmonics, not just the fundamental. For digital data and clock signals, you should be thinking out to at least the 10th harmonic. It's really driven by the rise and fall times. If they are longer than 1/10 of the signal propagation time from the source end to the load end, then you need to treat your circuit element as a transmission line. Any interconnection between a source and a load will consist of two conductors, a send or positive conductor and a return or negative conductor. The two conductors will have capacitance between them, defined as the charge stored divided by the potential between them, and the capacitive reactance, or impedance, is equal to 1 over j omega c. Where there is capacitance, a displacement current can flow, equal to the capacitance multiplied by the time rate of change of the potential. And where there is current, there will be magnetic flux coupling through the loop between the conductors. Where there is magnetic flux, there is inductance, defined as the magnetic flux per unit current that caused it, and the inductive reactance, or impedance, is equal to j omega L. We generally simplify our equivalent circuit to put all of the inductance on the positive side as shown here. And this forms our lossless transmission line model. This lossless model is the ideal, and it is an excellent and useful model in many cases, but in the more complete model, the conductors will have some non-zero resistance in series with the inductance, and the dielectric will have some non-zero conductance in shunt with the capacitance. Because the resistance and conductance terms represent loss in the line, this is called our lossy transmission line model. This is a general-purpose model that is completely independent of geometry. In the general transmission line model, the resistance, inductance, capacitance, and conductance are all per unit length. Thus, they are called the per unit length parameters, typically expressed per meter. This forms what we can call a unit cell of our transmission line over some infinitesimally small length delta z, and we can put a bunch of these unit cells in series to form a transmission line of some finite length. This unit cell provides the basis for understanding the behavior of signals propagating down our transmission line. We'll call the left side the input side and apply a voltage and current there called V of z and I of z. We'll call the right side the output side, and we'll also look at the voltage and current there called V of z plus delta z and I of z plus delta z. The voltage drop across the unit cell must be equal to the current I of z multiplied by the per unit length series impedance terms R plus j omega L multiplied by the length delta z. We can reverse the order of the voltage terms on the left side, put a negative sign out front, and divide both sides by delta z. We take the limit as delta z approaches 0 to get the negative of the derivative of the potential with respect to z equals I of z times R plus j omega L. Next, we apply Kirchhoff's current law, which states that the difference between I of z and I of z plus delta z must equal the current through the capacitance and shunt conductance, which equals V of z multiplied by G plus j omega c times delta z, where j omega c is the reciprocal of the capacitive reactance and is called the admittance. We follow a similar approach to get that the negative of the derivative of the current with respect to z equals V of z times G plus j omega c. This pair of equations will be a recurring theme in the rest of this session, and they are worth taking a moment to internalize. And they make intuitive sense. The spatial derivative of potential at a point on the line equals the current at that point times the series impedance terms, and the spatial derivative of the current at a point on the line equals the potential at that point multiplied by the shunt admittance terms. They really are just localized versions of voltage drop and Kirchhoff's current law. Now let's take this pair of equations and take the negative derivative of each one with respect to z. This gives us minus di dz on the right side of our first equation. We have an expression for that in the starting version of our second equation, and we'll make that substitution. Similarly, we have minus dv dz on the right side of the second equation. We have an expression for that in the starting version of our first equation, and we'll make that substitution. Now both equations include the same expression for the product of the series impedance terms and the shunt admittance terms. We will define the term gamma to be equal to the square root of the product of these terms. While it may seem a little weird and arbitrary to take the square root of this expression, there is a specific reason for it. This term gamma is called the propagation constant because it defines how the signals propagate down our transmission line. It also facilitates the math. We can substitute gamma squared into each equation, and we rearrange terms to get a pair of equations that state that the second derivative of the parameter of interest, voltage or current, minus gamma squared times the same parameter of interest equals 0. Equations of this form are called wave equations because they describe the propagation of the signal of interest as a wave in space. Each wave equation has a general solution that includes an amplitude term, V0 and I0, multiplied by e to the minus gamma z. Remembering the properties of exponential functions and their derivatives from the math sessions, we can differentiate each general solution twice to show that yes, indeed, each one satisfies its respective wave equation. In general, the propagation constant gamma may be a complex number with a real part alpha and an imaginary part beta. Alpha is called the attenuation constant, and beta is called the phase constant or the wave number. We can substitute alpha plus j beta for gamma, and we can separate the real and imaginary parts. Looking at the imaginary term, we'll recall Euler's formula from the math sessions and take the real part to give the magnitude term V naught or I naught times the attenuation term e to the minus gamma z times the cosine of beta z. These equations clearly represent a sinusoidally varying potential and current in the plus z direction, which is the direction of propagation along our transmission line. Let's focus on the equations for potential, and we'll set alpha equal to 0 for a lossless line for simplicity. So far, we have looked only at spatial variance, but now we need to look at time variance as well. At the source end of our transmission line, which we'll call z equals 0, we will apply a stimulus potential that varies sinusoidally in time. This is the electrical equivalent of wiggling the rope that we discussed earlier. Our stimulus potential will have the full exponential form given by the amplitude V0 times e raised to the power of j times omega t plus some starting phase theta, and the real part is V0 times cosine of omega t plus theta. In this example, we will set our starting phase to minus pi over 2 so that the starting potential is 0 at time t equals 0, much like our rope will likely have 0 displacement at time equals 0 until we start wiggling it. The phase does not significantly affect the following discussion, but we'll include it for completeness. The response of the potential along our transmission line will be a function of both position z and time t, and it will have the full exponential form of V0 times e raised to the power of j times omega t plus theta minus beta z, and the real part is V0 times cosine of omega t plus theta minus beta z. We can now focus on the cosine version of this expression, and we'll move the theta term to the end of the cosine argument. And now we're ready to apply our stimulus signal. At time t equals 0, our stimulus potential is 0. If we look only at our stimulus signal at the source, where z equals 0, we will see it varying sinusoidally in time as we have defined it. Now we'll look at how the time variance of our stimulus signal combines with the spatial variance along our transmission line. When we advance in time by a quarter of a temporal period, which corresponds to omega delta t equal to pi over 2 for a quarter cycle, two significant things happen. The signal level at z equals 0 reaches its full amplitude of V0, while our starting level of v equals 0 propagates outward from the source by some distance delta z. Thus, this point in space is at the same potential that the point at z equals 0 was a quarter cycle earlier. This means that this point with constant potential, and indeed the entire waveform, is propagating in the plus z direction. Because V0 is a constant, the potential can be constant only if our cosine argument is constant. Because theta is constant, omega t minus beta z must also be constant. For this to be true, any change in our time-dependent term, omega delta t, must be balanced by the same change in the spatial-dependent term, beta delta z. Thus, if omega delta t equals pi over 2 for a quarter cycle in the time domain, then beta delta z must also equal pi over 2, such that the waveform advances by a quarter cycle in space. If we advance in time by another quarter cycle, we also advance in space by another quarter cycle. If we advance in time by a half cycle, given by omega delta t equal to pi, we also advance in space by a half cycle, given by beta delta z equal to pi. And if we advance in time by a full cycle, where omega delta t equals 2 pi, we also advance in space by a full cycle, where beta delta z equals 2 pi. And so on. The distance between consecutive peaks on the waveform is called the wavelength, designated by the Greek letter lambda. The wave number beta is defined as 2 pi divided by the wavelength. We can compare this to the angular frequency omega, which equals 2 pi times the temporal frequency f, or 2 pi divided by the temporal period, capital T, which is the reciprocal of f. From this, we see that the relationship between wave number beta and wavelength lambda directly parallels the relationship between angular frequency omega and temporal period t. Previously, we noted that omega delta t must equal beta delta z. Rearranging terms, we see that delta z over delta t equals omega over beta. Taking the limit as delta t approaches 0, we get dz dt, which is the velocity of propagation of our wave along our transmission line, denoted by the letter u. Thus, the velocity of propagation equals omega over beta. Given the relationships for beta and omega, it can also be expressed as the wavelength lambda divided by the temporal period t. This makes intuitive sense because it says that the wave travels one cycle in space, defined by the wavelength, during one temporal cycle, defined by the period. Because the period is the reciprocal of frequency, this can also be expressed as the wavelength multiplied by the temporal frequency. From this, we can rearrange terms to get this useful relationship, which states that the wavelength is equal to the speed of propagation divided by the temporal frequency. Doing a quick dimensional analysis, we can express speed in meters per second divided by frequency in cycles per second. The per second terms cancel, and we're left with meters per cycle, which is the wavelength. This relationship between wavelength, speed of propagation, and frequency is central to everything we do with transmission lines. Indeed, it is the very reason that transmission lines exist. A finite speed of propagation leads to a finite wavelength, and as frequency increases, the wavelength decreases. And as I said at the beginning of this session, when the length of a circuit element is a significant fraction of a wavelength, it will behave as a transmission line. So, here we are, and this will be another recurring theme going forward. As we just discussed, a stimulus potential that varies sinusoidally in time will produce a potential that varies sinusoidally in space along the length of our transmission line. When the line is electrically short, that is, when it is shorter than 1/10 of a wavelength, the signal amplitude does not vary significantly over the length of the line, and we can treat it as a lumped element. When the line is electrically long, that is, when its length is a significant fraction of a wavelength, the signal amplitude clearly does vary over the length of the line, the lumped element model no longer works, and now you have to treat it as a transmission line. For a lossless line with an attenuation constant alpha equal to 0, the peak amplitude of the signal stays constant as it propagates down the line. For a lossy transmission line with non-zero attenuation constant, the peak amplitude will be attenuated inside an envelope defined by V0 times e to the minus alpha z. This is precisely what is meant by a lossy transmission line, that the signal amplitude decreases as the wave propagates down the line. Let's go back to our propagation constant gamma. For a lossy transmission line where the R and G terms are non-zero, extracting the real and imaginary components is clearly non-trivial. Both terms are frequency dependent. Beta is addressed on the next slide, but regarding alpha, we expect the attenuation to increase with frequency. Taking the example of a digital waveform with fast rise and fall times, the transmission line will act as a low-pass filter that will round the edges and distort the waveform. For a lossless transmission line, where R and G are equal to 0, the propagation constant simplifies to j omega times the square root of LC. In this case, gamma is purely imaginary, which means alpha equals 0 for no attenuation in a lossless line, and beta equals omega times the square root of LC. We rearrange terms to show that omega over beta equals 1 over the square root of LC. Well, recall from the preceding discussion that omega over beta equals the velocity of propagation u, which means that the velocity of propagation on a lossless transmission line equals 1 over the square root of LC. Recall that for a uniform plane wave propagating in space, the velocity of propagation equals 1 over the square root of mu epsilon. The permeability mu is expressed in units of henries per meter, inductance per unit length, and the permittivity epsilon is expressed in units of farads per meter, capacitance per unit length, giving the same general form as the expression for our transmission line. We'll come back to this in Part 2. The characteristic impedance of a transmission line is defined as the ratio of the potential to the current looking at some point on the line, and it is generally designated as Z0. We'll start with the general expressions for potential and current, then we'll recall our workhorse equations for their derivatives from earlier in this session. We take the negative of the derivative for our expression for V of Z to get gamma times V of Z, substitute it into the left side of our first equation, rearrange terms to get that the ratio of potential to current equals our series impedance terms, R plus j omega L, divided by gamma. And the ratio of potential to current is the definition of the characteristic impedance, Z0. We apply the same set of steps to the second equation to get that the ratio of the potential to the current equals gamma divided by our shunt admittance terms, G plus j omega C, and this also equals Z0. Recalling the definition of gamma, we can substitute it into either one of these equations to get that the characteristic impedance of a lossy transmission line equals the square root of the series impedance terms, R plus j omega L, divided by the shunt admittance terms, G plus j omega C. For a lossless transmission line, the R and G terms go to 0, and the characteristic impedance simplifies to the more familiar square root of L over C. In the real world, of course, all transmission lines are lossy, and you need to know the full expression when it's needed. But in many cases, the lossless simplification is sufficient, at least as a starting point, and it's clearly easier to work with. Recall for a uniform plane wave, the characteristic impedance is equal to the square root of mu over epsilon. Again, looking at units, this is in terms of inductance per unit length divided by capacitance per unit length, giving the same form as the expression for our transmission line. This will wrap up Part 1. In Part 2, we'll take a look at some common transmission line configurations used in the real world, and we'll take a deeper dive into the behavior of signals on transmission lines with emphasis on what can happen when you don't take these behaviors into account. See you in Part 2.